Okay, so we're just going to continue working through this review that we didn't quite finish in class. So question 12, using the periodic table, identify two physical properties of the element zinc. So zinc is over here, and this is in this middle chunk. And if you look at review 1, we had talked about these being the transition metals. And transition metals are the metals that we typically think of when we think about metals. So copper and nickel and iron are all in here. So if we think about metals, typically we think about things that are hard, that are shiny, that are dense, that perhaps are magnetic or conduct electricity. So those are all different physical properties. So, whoops, switch to draw here and just go with a darker color. So hard, dense, shiny, maybe something that you had good conductor, so both of heat and electricity. And you may have had some other properties as well that you had. Question 13, from your experience, describe two chemical properties of the element oxygen. So chemical properties are ways in which the element oxygen reacts. So oxygen is a very reactive element, and two different ways that it reacts. So one is that it is combustible. So in grade 10 science, we looked at combustion reactions, which were different types of gases when combined with oxygen would create carbon dioxide and water. So we're going to learn in grade 12, and for you, if you take that, organic chemistry are molecules that are made primarily of carbon atoms with oxygen, nitrogen, and hydrogen atoms as well. And so it is hydrocarbons that usually are the things involved in combustion reactions. And then another way that oxygen reacts chemically is that it will combine with different compounds to decompose. So when things rot, it is because of a reaction with oxygen. So we'll just write decomposition, which is also a type of reaction where things break down. And that doesn't necessarily have to include oxygen. So remember, decomposition reaction is where one larger molecule breaks into smaller ones. This type of decomposing we're talking about is not a decomposition reaction where one thing breaks, but where something combines with oxygen to break down. And so I'll just put in brackets here that we're talking about something rotting, decomposing in that sense, not in terms of the classification of reaction where we only start with one reactant. Okay, Bohr-Rutherford diagram. So most of the time you have probably seen them drawn like this. Now, yesterday we talked about how in the center we would draw or identify the number of protons and number of neutrons. So these diagrams here aren't drawn fully complete because they do not identify the protons and neutrons here. So we are going to determine what element we have here. And so I'm going to go to my periodic table and I'm looking for something. So there are 3 shells of electrons, which means this element is found in the 3rd row. And in the valence or outer, the furthermost shell, the electrons has 2, 4, 6, 7. So I'm going to go to group 7. So 3rd row and group 7. So 1, 2, 3 down, and 1, 2, 3, 4, 5, 6, 7. So that element is chlorine. And the symbol for that is Cl. And remember, when you do your symbols, if something is one letter, that letter is capital. If something is 2 letters, and occasionally in those rows in the very bottom, sometimes there are 3 letters for a symbol. The first letter is capitalized, the subsequent letters are not capitalized. So how we tell when we look in a compound if we have a new element is if we have a capital letter. Every time we see a new capital letter, that signifies a new element. So we need to be careful not to write C capital L. Okay, the next one has 2 shells of electrons, and there are 6 electrons in the outer shell. So I'm looking to the second row and the 6th, so 3, 4, 5, 6. So that one is oxygen. Okay, now I have ions. So I'm going to figure out where I am based on the valence electrons here. And then from there, if something has a charge of 3+, it has more protons than electrons, which means electrons must have been lost. So right now there are 2, 4, 6, 8, 10 electrons. So that's 10 negative charges. To end up with a positive charge overall, I must have 3 more positive charges. So 13 protons. So that's what would give me an overall charge of 3+. So I can just look for whatever has the atomic number of 13. That periodic table I'm looking at, I don't think was showing it that way. So I'm going to go back to the periodic table that we have listed in here. And so I am looking for 13, which is aluminum. And the Bohr diagram was showing 2 full shells, so that brings us to here. And 3 electrons were lost, so 1, 2, 3 electrons. So that's another way we could have found that it was aluminum. Whoops, I forgot here that we were still working in OneNote. So this is aluminum, and it's an aluminum ion with a charge of 3+. So the next one here, we have an overall charge of 2-, and I have in this one as well 2, 4, 6, 8, 10 electrons, and the overall charge is more negative by 2, so that means that I have 2 more electrons or 2 less protons to get that charge. So I am looking for an atomic number of 8. And that is over here, oxygen. Whoops, did it again. Okay, there we go. So this is oxygen, and it's an oxygen ion, so we're going to put the charge in 2-. Okay, significant digits. So we talked about this yesterday. I'm not sure if you have covered this in a previous science course or a math course. So significant digits has to do with the total number of numbers that we deem to be important here. So if I think about a measuring device, if I have a ruler, most of the rulers that we have, so if I have it in centimeters, it will show millimeters. So it'll kind of show the halfway point. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So as I'm measuring something in centimeters or millimeters here, I can go to the nearest 1/10 of a centimeter or to the nearest whole millimeter, and then I can guesstimate in between. So if I have something that falls maybe over here, that is in between 1, 2, 3, and 4. So I might say that that is 3.5 millimeters. Now, the way I've drawn it here, it's not very obvious at all because that line is quite thick. But if you could see, so if we were looking at this was millimeter 3 and this was millimeter 4, and I was over here, then I'd say that's about the halfway point, and it looks close to halfway between there, or a quarter of the way, maybe a little bit more than that. So this is where you would say that is maybe 3.25 millimeters or 3.3 millimeters. So here we can't go beyond that in terms of being accurate in our measurement. So our measuring device will tell us how precise we can be, which is how many decimal places or how many numbers in terms of place value we can go in accuracy. So when I see something that is 135 millimeters here, it doesn't show me any decimal places. So here I have 3 numbers. So I have 3 significant digits. In the next one, so our last number, we often round. So 135 millimeters over there. If my measuring device went down to millimeters, I could have estimated there a decimal place. So was that in between 135 and 136? And so then I would have put that down. And because they don't have another place value there, my assumption is that my measuring device only measures to there, and then I'm guesstimating that last number. So here, when I have a 0 at the end of a whole number, this one's a little bit tricky because I'm not actually sure if I have 1 or 2 significant digits there. So we're going to get into this in more detail in this course and in grade 12. So for our purposes right now, for 20 students there, that one is fine to say that is either 1 or 2 significant digits. Now, in terms of a context, 20 students, that one, I think it is fair to say that's 2 significant digits, that both the tens place and the ones place. Students, we can only have whole students. And so that one, with the context, we can make that assumption. Okay, when we have decimal places, any zeros that are given after a decimal place are all seen as significant digits, because that tells us that I could have been measuring numbers here in the tens and hundreds place values, but this was exactly at 4.00. So here I have 1, 2, 3 significant digits. Over here, when I have zeros after a number in a decimal place, those are significant, but the numbers zeros to the left of a number are not deemed to be significant. So here I have 1, 2, 3 significant digits. 6.02 times 10 to the 23, that's going to be a constant that we look at later on in Unit 3. So there I have 1, 2, 3 significant digits. So when I have a 0 in between numbers, it counts. When I have zeros after a number, but it's still a whole number, those don't have to count. But when they are after the decimal place, then they do count. So zeros get a little bit tricky in terms of whether they count or not. So to the right, if we are in the decimals, they count. If we are not, then we're not sure. And so often we specifically would write this using scientific notation if that 0 is significant or not. And then anything that comes to the left of a number is not significant. Whoops. So in this last question, 5.70 liters, the 0 comes in the decimal place to the right, and so that's significant. So I have 1, 2, 3 significant digits here. Okay, and our last question here. So we are going to balance these equations and then write the word equations. So I have 1 potassium, 1 potassium, 1 chlorine, 1 chlorine, 3 oxygen, 2 oxygen. So here I have sets of 3 and sets of 2. So I need a number that 3 and 2 can both go into, which is 6. So I can get 6 oxygen in my products by having 3 molecules of oxygen. And on the reactant side, I can get 6 oxygen atoms by having 2 molecules of potassium chlorate. That is going to leave me with 2 potassium and 2 chlorine, which 2 potassium chloride will balance out. So on each side, I have 2 potassium, 2 chlorine, and 6 oxygen. So this is now balanced. Naming the chlorate, you quite possibly don't know how to name yet. This is found in your periodic table. So we have this section called My Best Friends, and these are all going to be very helpful to you. And you always get these in 3U and 4U on any assessment, including exams. So polyatomic ions you probably went over in grade 10. We will be going over again here next week or the week after. And these are just all of the, so poly meaning more than one type of atom that band together as a unit and work as an ion. So ClO3 is called chlorate, and it will make a ClO3 minus ion. And so that in this question goes with potassium, which becomes a plus. And so the plus and minus then are attracted to one another to make that ionic bond. So I have potassium chlorate So we will go over this naming. So that is going to decompose to become potassium chloride. So this one, hopefully you remember from grade 10, but we will start with these when we're going over naming. So ionic bonds, we have the name of the metal first, stays as its full name, and then the name of the nonmetal. We drop the ending of the name and put "ide" at the end. So chlorine becomes chloride. And then oxygen is just the name of the element. And remember, we talked about Hofbrinkel today. So O is part of Hofbrinkel. So that's one of the diatomic molecules that we are going to need to remember. But Hofbrinkel will help us to remember that. Okay, next one we have iron reacting with oxygen to produce iron oxide. So I have here 1 iron, 2 iron. So a 2 in front of here could fix that. And then 2 oxygen and 3 oxygen, and that one's not so simple. So once again, groups of 2, groups of 3. So 6 total oxygens is what I'm going to need to have there. So 3 groups of 2 here, 2 groups of 3 here, so that'll give me 6 oxygen on both sides. I now have 4 iron in my products, and so I'm going to need 4 iron in the reactants. So this was, oh, and I made a mistake here. So this should be a plus, and this should be our arrow. Okay, so we have iron reacting with oxygen to produce iron oxide. Now, iron, if you recall from last year, is something called a multivalent ion. And so if we look back to that periodic table, multivalent metals are part of our best friends. And iron over here can be a 3+ or a 2+. So we in 4U will get into details about multivalent ions. If you take a look at all of the different names here and look up where they are found. These are generally found in the area of the periodic table that are called transition metals. And so a lot of these have what is called multiple valences. And so that means sometimes iron has 3 electrons in its valence shell that it will lose, and sometimes it has 2 electrons in its valence shell. And that has to do with, as we get into the different shells of electrons, the locations of the electrons are not necessarily found the way that I'm just going to move over here to our Bohr diagrams. The way that we, up until grade 10, have been looking at our different electron shells. So up until grade 10, we've talked about 2, 8, 8. And when we did the first 20 elements up to calcium, that just takes us to 2 electrons in that 4th shell. And it's after that that where exactly the electrons are found within that shell changes. And we won't actually get into really details about this and why this is until grade 12. But for now, I'll just say that electrons are found in different regions, and the probability of finding them in a certain area makes a certain shape. And so we have different regions within any shell that, so we have multiple regions in each of the different shells where electrons can be found. And some of those regions take more energy to fill an electron in that space than to actually fill an electron in the next shell. So the reason that iron can have either 2 or 3 electrons is that one of those electrons will sometimes be found, and I'm just going to quickly move to the periodic table. So iron is found in the 4th row here. And sometimes one of the electrons is going to be found in actually the 3rd level, and sometimes one of those electrons will fill the 4th shell because it takes less energy to do so. And so sometimes there's 2 electrons and sometimes there's 3 in that valence shell, which is a bit of a weird thing. But once again, we're going to get into that in more depth. And there's a lot of diagrams and things that will help it make sense. But for now, you just need to know that there are certain atoms that can gain or lose a different amount of electrons. So here, iron can lose either 2 or 3. And if you remember crisscross to figure out the chemical formula of an ionic compound, we can do reverse crisscross to work backwards to figure out the valences. So that means iron would have had a 3+, oxygen would have had a 2-, and oxygen is indeed a 2-, so that means that this would have been an Fe3+, or what we would call iron 3 oxide. So hopefully this is coming back from grade 10, that when something is multivalent, we are going to identify which valence it is with Roman numerals. So this one is iron 3 oxide. We are going to go over this naming as well as part of Unit 1. So if it's not fully coming back, don't worry about that. Okay, the last one we're going to look at, we have a single displacement here. So magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen gas. So I have 1 and 1 magnesium, 1 and 2 hydrogen, and 2 and 1 chlorine. So I have half the number of chlorines and hydrogens on this side. So a 2 here will give me 2 hydrogen, 2 chlorine, and still the 1 magnesium. So done for balancing. Like I said, we have magnesium and hydrochloric acid. We're going to go over in our first unit how to name acids. So right now you may recognize hydrochloric acid. There may be a couple more you recognize, but we're going to go over the specific rules. And once again, there's information on our best friends page there that you get for all assessments. So you don't have to memorize things. There's certain things you'll have to remember, but the sort of base where we come up with the names from is all on there. So you just have to kind of remember a couple of rules, and then for all the different acids, based on those rules, there's information in there. So here, if you're looking at just the way of naming otherwise, you might have called it hydrogen chloride. Okay, then we have magnesium chloride and hydrogen gas. Although we're just going to call it hydrogen, so we don't add the gas in. If we have a written sentence, we would write hydrogen gas, but in our word equation, we don't include that. All right, and that's everything for the review.